In this lecture, we're going to do one of the more time-consuming factorial ANOVAs, which is one that has two dependent factors. So in this ANOVA, there are two factors with at least two levels each, and both factors are dependent. So the factorial ANOVA with two dependent factors is kind of like an extension of a repeated measures ANOVA, except now instead of just dealing with one independent variable, you're dealing with two independent variables. So here's our example. Researchers want to compare the anxiety levels of 6 individuals at two marital states after they have been divorced, and then again after they have gotten remarried. So anxiety is measured at 3 times, week 1, week 2, and week 3. Anxiety is rated on a scale of 1 to 10, with 10 being high and 1 being low. Use alpha 0.05 to conduct your analysis. We're going to see if there are any differences anywhere. So we have one dependent factor, which is week. We're measuring the same person at 3 different times, week 1, week 2, and week 3. So that's going to be some kind of consistent relationship between those 3 levels because we're measuring the same people. We also have another dependent factor, which is divorced and married. We're measuring the same people just after they got divorced and then just after they got remarried. So there's also going to be some consistency between these two groups because we're measuring the same people. Now it's kind of hard to display in a table two dependent factors like this, but realize that everything I have in red right now is the same person. We have subject 1 measured 1, 2, and 3 weeks after they got divorced, and we also have subject 1 measured 1, 2, and 3 times after they got married. So there are really only 6 people in this analysis. There are 6 individuals, even though we have 36 total scores. So let's do a hypothesis test with our 7 steps, starting with defining the null and alternative hypotheses. So here we're going to have 3. We're going to have 1 to test to see if divorced and married are any different. We're going to test to see if there's any difference between the 3 weeks. And we're also going to test to see if an interaction is present or not. Next, we're going to state alpha, which is easy. I just said use 0.05. And now we're going to calculate the degrees of freedom. So first, let's get a look at what we're going to be dealing with here. This is going to be our source table. We're going to have our 3 effects, marital status, which is A, week, which is B, and the interaction, A times B. And we're also going to have total. Now, we're also going to have 4 different error terms, because remember, all the factors are dependent. So we're going to have 1 error term associated with A, 1 associated with B, 1 associated with the interaction between A and B, and 1 all by itself for consistent subjects variability. So looking at this, we have 8 different sources. So that means we're going to start by calculating 8 different degrees of freedom. These are our 8 degrees of freedom, and these are our equations. Now, none of this should be too hard, we're just plugging stuff in. Realize that I'm using capital N, which is going to be 6 because there are 6 scores in each cell. Depending on what class you're taking or who you're taking it with, they might use a lowercase s, lowercase n. I mean the same thing here. So here we calculate our 8 different degrees of freedom. And you can see that they all add up to 35, so we know we did it right. Next, we will state our decision rule. Realize we have 3 hypotheses, so we're going to have 3 decision rules. And in order to find these decision rules, we're going to use degrees of freedom for the effect and degrees of freedom for the error. So for marital status, we're going to use 1 and 5. And for week in the interaction, we're going to use 2 and 10. So that means we're going to head to our F table, and we're going to look up, well, on the top we have between, on the side we have within. And first we're going to start by looking up 1 and 5. We're going to find a critical value of 6.6079. So that's going to be our critical value for marriage. We're going to use 6.61 for marital status, sorry. And now we're going to go back and look up 210, and we find a critical value of 4.1028. So our critical value for a week and marital status by week are going to be 4.10 and 4.10. So those are our decision rules. For marital status, if our F is greater than 6.61, we're going to reject the null. And for weak and for the interaction, if our f's are greater than 4.10, we're going to reject the null in those cases. So let's actually start calculating some f's. We're going to calculate our test statistic now. So realize we have this table. We need to find 8 different sums of squares. We need to find a times b, the 4 different error terms, and the total. It's a pain, so let's get started. First, we're going to do marital status. That should look pretty similar to what we've done before with our other factorial ANOVAs. What we're going to do is we're going to take the sums at each level of A. So adding together all the scores at divorced will give us 93. Adding together all the scores at married will give us 84. And that's going to go on the top of the equation. We're going to have 93 squared plus 84 squared. Then we're going to divide by b by n. B is 3 and n is 6 because there are 3 B groups and there are 6 people in each cell. That's easy. Capital N is 36 because we have 36 scores. And capital T is 177. It's just all the scores added together. So doing all of that, we find a sum of squares marital status of 2.25. Next, we're going to do weak, which is kind of like marital status. We're just flipping around the A and the B, so it's not that bad. And we already know T squared over N, so we don't have to do a whole lot of work there. So we're going to start by finding our week 1 sums, our 3 different levels of week. So for week 1, we have 30. For week 2, we have 53. And for week 3, we have 93. So that goes on the top of the equation, 30 squared plus 53 squared plus 94 squared. And we divide by a and n, which we already know. And we already know t squared over n. So working that out, we find a sum of squares week of 175.17. Next, we have the interaction of marital status and weak. Now that's pretty easy. Remember, we already have the last 3 parts of this equation. So we put that in there. We just need to find the first part. So the first part is referring to each AI at each BI, each level of A at each level of B, and vice versa. So we're going to look at the cells at A1, B1, at A1, B2, A1, B3, B1, you know what I mean, every single cell. So we have 6 total cells here, and we have 6 total cell sums. We have 22, 8, 27, 26, 44, and 50. So on top, it's just going to be us squaring those numbers, then dividing by n, which is 6. So I've got to move on, but if you do work that out, you get a sum of squares interaction of 17.16. And now we're going to do total because that's pretty easy. We already know the last part, we just need to find sum of all y squared. Sum of all y squared is just every single score squared and then added together. So our sum of y squared is 1081. So our sum of squares total is 210.75. And there we go. There's our source table with the 4 sum of squares we found so far. Now we're only halfway done. We still have to find 4 more sums of squares for all 4 error terms. So let's start with sum of squares error for A by S. A by S is going to look something like this. Realize that we already know a lot of this stuff. We know the second thing and the fourth thing. We just need to find the first fraction and the third fraction. So this one right here, what we're going to do is we're going to add up all of the scores of each individual and then divide by A times B. So you see I have the different colors in my table. We're going to add up all the red scores, and that's one sum because they come from the same person. We're going to add up all the green scores. That's one sum that comes from one person, and so on. So we're actually going to have 6 sums here because we have 6 subjects. So we have our 6 sums, 30, 30, 28, 30, 29, and 30. And we just put those into the equation. We're going to square those and then divide by A times B, which is 2 times 3. Easy. Now we have to find the first fraction, which is each AI NI squared added together divided by B. So we're going to find each subject's sum at each level of A, which you can see I've done in the table. For example, subject 1 at A1, which is divorced, is just 3 plus 5 plus 7 is 15. And we go down and we find all of those sums. We find our 12 different sums. So on top of the fraction, we're going to take those 12 numbers, we're going to square all of them, add them together, and divide by b, which is 3. So when you work through this whole crazy equation, we find a sum of squares error for a by s of 1.25. Now we're going to go back to sum of squares error for b by s. And we've already found 3 of these things, right? We can put them in there, that's easy. We just need to find the last part. Now, the last part is referring to the sum for each subject at each level of b. So what that means is we have subject 1 at b1. That would be 3 plus 1, right? Subject 1 at b2 would be 5 plus 5. Subject 1 at b3 would be 7 plus 9. Subject 2 at b1 would be 4 plus 2, and so on. So you're going to find a lot of those numbers. It's actually going to look something like that. You're going to take all of those sums, you have a ton of them, you're going to take all those sums, square them, add them together, and divide by a, which is 2. And after working through that whole mess, you get a sum of squares error b by s of 9.4. Now we're getting pretty close to being done. We just need to find sum of squares error for subjects. Now this equation should be pretty similar, pretty simple. We've already found all that stuff, right? We don't need to do any additional work. We just have to plug in stuff we've already found. And we get our sum of squares error subjects of 0.58. So look at that. We have 7 of the 8 sum of squares that we need. And lucky for us, we don't have to calculate the last one the long way. We can do it the short way. We just take the total and subtract everything we found so far. And whatever's left over has to be our last term. So that's how we get 4.94. We take 210.75, subtract everything from it, and what's left over is 4.94. Now we need to find our mean squared, which is not that bad. It's just our sum of squares divided by our degrees of freedom. So we find all those. Like for marital status, we just take 2.25 divided by 1, we get 2.25. You just divide across. Not too much work. Pretty good. Now that we have that, we have to find our 3 f's. F is found by taking the ms of the effect and dividing that by the ms of the error that is associated with that effect. So for A, we're going to take 2.25 divided by 0.25. For B, we're going to take 87.59 divided by 0.94. And for the interaction, we're going to take 8.58 divided by 0.49. So we have 3 f's, 9, 93.18, and 17.51. We did all that work just for those 3 values. And now we can state our results. For the first hypothesis for marital status, we're going to reject the null hypothesis because our F was 9. For weak, we're going to reject the null because our F was 93.18. And for the interaction, we're also going to reject the null because our F was 17.51. All 3 of those F's were greater than their critical values, so we reject all 3 null hypotheses. And our conclusion is that anxiety levels differed significantly for divorced and then remarried individuals. There was also a difference between the anxiety levels of the 3 different weeks, and an interaction effect was also present. If you're still with me, that was a factorial ANOVA with 2 dependent factors.